Okay. All right, so let me start that recording. And then let me share my screen here so that I can project this. Looks like it's installing a new plugin. Give it a second. Good, there it goes. And then also, let me write down here, chapter 34, number 12. Okay. Nice. Sure, it comes into focus. All right, nice. Okay, now let's read that one together. Let's see. I called all this stuff up ready for this. Here we go. All right, so number 12 says what? Verify by substitution. Am I reading the right one?
Yes.
Okay. That the equations of the solution, so I think 3415 and 3416 are, well, let me not guess. Run over here and grab the book and say, I think those are the wave equation ones that he worked out. 34, 15, let's see, equation 30, 26, 21, 9, 15. So let's start here with this one, 34, 15. And it says, if you take the partial derivative of the electric field with respect to the x-axis twice, you will get mu naught epsilon naught multiplied together, and then the second derivative of the electric field with respect to time. And I'll just write that one. The other equation just has magnetic field here, but they give you this equation for the electric field, that some constants that then oscillates according to this mathematical equation. All right, now there's a little buried in this mathematical equation that you may not be as familiar with, because this K and this omega, I think will be needed here. The K, called the angular wave number, it's 2 pi over lambda, and omega is 2 pi times the frequency. Now, I guess recently we've been doing a lot with omega, the angular frequency, so maybe that's not a surprise, but the angular wave number could be, because this is covered in great detail in the chapter, must be chapter 16, which is covered in Physics 123. So I feel like I need to say that here in the beginning, because half of you students have done Physics 123 and the other have not. And the way we have our program is, we kind of skip over those chapters and do 122 and then come back to them in 123. So that I feel like I better pause and spend a little bit of extra time on. So you'll see how that'll come back into play here, and we'll need that here in just a second. But in the meantime, let me go ahead and take the derivative twice. Maybe I should just do it once the first time. Okay. With respect to x. So when you take the derivative of this function, you leave the constants alone. The derivative of a cosine becomes, I believe it's negative sign. So it would be,
Yes.
okay. So I'll put a negative out in front and then put a sign. And it's then the same argument, kx minus omega t. The chain rule would say take the derivative of the inside piece, and it says with respect to x. So the second term doesn't have an x in it, so that derivative would be 0. But the derivative of x is just 1, so that would leave a k. All right, so now if we do that a second time, and I'll do the minus, and I'll do the k, and I'll do the e maximum. So those are all constants. So now I'm going to take the derivative of a sine function. Well, derivative of sine is a cosine. Same arguments. And then the chain rule would say take the derivative of the piece inside. So again, that's another k. So I'll put a k squared. Again, the partial with respect to x, derivative of x would be just a 1. So there's a k left over. And then this has no x's in it, so that'd be 0. All right. So that's the part that I'll put on the left-hand side of the equation. Let's go ahead and take the derivative with respect to time of this. Okay, so same logic, a constant you would leave alone. You would take derivative of a cosine and a minus sign with the same arguments. Then the chain rule would say, all right, take the derivative of the inside piece. And now, in this case, the part in the front with the x's, that would be 0. And this part with the time would leave me with a negative omega. So I'll put a negative and then an omega. So let me do it now a second time. Right, so the plus omega e max, those are all constants, leave those in front. Taking the derivative of a sine is a cosine, same arguments. And then chain rule would give me a negative omega. So I'll change that to a negative out in front and square the omega. All right. So now that I have the second derivative with respect to time and also the second derivative with respect to space, I'll put those together. So the left-hand side of this equation is minus k squared e max cosine. And to save a little space, let me not write that in there. I'm just going to put cosine of that stuff. Because on the other side of the equation, I get mu naught epsilon naught. And then this is the second derivative with respect to time. So that would be a negative omega squared, an E max, and a cosine of that same stuff. All right, so there's the question. This is the gist of the problem, how the author says. He says verify. So verify, that's what you're doing. You're putting everything in the right-hand side of the equation, everything the right, and you're seeing if they match. And let's see, they each have a negative, so I'll get rid of that. They each have a maximum electric field. I'll get rid of that. They each have a cosine function with the same argument, so I'll get rid of that. And so we've got a k squared, and then we've got this mu naught epsilon naught omega squared. And that, brings up the question, does this match that? And that's why I was saying we kind of need to know what, particularly this angular, what's the word? Angular wave number is what it's called. And then, of course, the angular frequency. So let me put those in. So coming back up to here and putting this 2 pi over lambda squared, this would be 2 pi over lambda squared. This would be mu naught and epsilon naught, and this would be 2 pi f squared. All right, now we're getting close. But it's something like this. You can probably see the 2 pi squared and the 2 pi squared would cancel. And so I'll get 1 over omega squared. Lambda squared over mu naught, epsilon naught, and frequency squared. Maybe I'll bring the lambda squared to the other side, because this, again, is the wavelength times the frequency, which is the speed of these waves. And it was commented that the speed of these is the speed of light. This was actually Maxwell's great discovery. I guess he kind of gives it away. I guess somewhere down on the same page a little further, C for the speed of light, there it is, speed of light equals wavelength times frequency. But he also says for this to work, then this should equal the speed of light. It's 1 over the square root of mu naught over epsilon. And so it does, if you will. So I could write then this as 1 over the speed of light squared. And then, of course, that equals 1. And so there would be your proof. Yes, 1 does equal 1. Convinced of that. So, yes, the left-hand side does match the right-hand side.
Thank you.
Yeah. And it sounds like you're good. I mean, I could do the B one too, but it's actually the exact same steps.
Yeah. I think I figured out where I was stuck.
Oh, okay. Good.
Right. That's it for me. Thank you very much, Professor.
Okay. You bet. Take care.
You too.
All right. So let's do this number 3. And I got to reshare here. That's connecting. Go to the questions. All right. So here is question number 3. Here is a good one here. It says, consider the situation as shown in figure 3. Okay, so, I better write this down. 1046. Okay, so number 3 has a picture that looks a little like this. It's got a small circular space, and they give it kind of an orange dots. And so I think they're meaning that's an electric field. And so I'll try to do this in orange. And so I've got these dots sticking up. And so the electric field is coming out. They even say electric field out of the paper in this area. And then they say the electric field is 0 a little further out. And then they ask for what is the magnetic field further out. And I say further out because they give a radius of 5 centimeters for where the electric field is pointing out. And they give a radius of 15 where there is this point P that they're trying to figure out what is the magnetic field. In fact, I'll read the words here. It says, so consider the situation shown in figure 3. An electric field of 300 volts per meter is confined to a circular area that is 10 centimeters in diameter. So I did the radius of 5. They're showing it as a diameter of 10. And is directed outward perpendicular to the plane of the figure. If the field is increasing at a rate of 20 volts per meter each second, what is the direction and the magnitude of the magnetic field at point P, 15 centimeters from the center of the circle? So again, here's this point P. And the crutch of this problem is really the final step for the semester, because we learned Ampere's law a couple of chapters back. Where was Ampere's law? Must have been like chapter 30. And then this chapter, the final chapter, says, well, there must be more to it. And so this is Maxwell's brilliant discovery. He says, look, there can't just be this term. And he argues it with capacitors and resistors. And I'll let you look at the book or my video to go back and argue why this can't be complete. And then he uses that to say, well, what would make it complete would be if you had another term that corresponded what we often call a displacement current, but it's really a changing electrical flux. And so as we read this math here, here's what we're really saying. This is really saying here that a magnetic field can be made for 2 reasons. The first one is that charges just flow and move along. And that's how we learned it first. That was chapter 29 and 30, Ampere's law. But now we're learning that a magnetic field could also be made by a changing, and so this would be the derivative, a changing an electric field. And so these are the 2 big pieces of our electromagnetics. We already learned that an electric field could be made for 2 reasons. The first was just from charges, and the second one was from a changing magnetic flux. So it doesn't surprise us that there would be 2 ways to make the magnetic field. And it wouldn't surprise us if those 2 were kind of the same as the electric field. These are the charges, and so charges, moving charges make magnetic field, just regular charges, stationary or moving, make an electric field. And then the second way of making the field is by the changing of the other field. So this one is saying that a changing electric field makes a magnetic, but Faraday's law said a changing magnetic made an electric. So we've learned the second way of making the fields, and they feed off each other. So electric fields can make magnetic fields, and magnetic fields can make electric fields, but only if they're changing. Anyway, so that's what's going on here. So what they're trying to say here is we have an electric field, and it is not a constant field, it is changing. They said it is changing at a rate of 20 volts per meter each second. And so this problem is along that idea that this is an electric field that is changing. And as a result of that, you must get a changing magnetic field. So here's how we solve it. We draw an Amperean loop, just like we would have drawn an Amperean loop where we had regular current. We argue some symmetry. And so maybe I'll do the dot product and argue some symmetry. And so this is where they kind of helped us in the drawing. They drew an Amperean loop for us. And so they draw this green line around here. But the integral, the ds along this line here, so this line integral, as we go around, this really is the path. And so there's the ds. And so the question is, what do we know about the magnetic field along this path? And again, here's where that symmetry comes into play. I guess the first bit of symmetry I would say is if I were to stand anywhere on this Ampean loop, the electric field that is changing would have the same appearance everywhere on this circle. And so the reason of picking a circle for the Ampean loop is if it all looks the same, whatever field is made at point P must be made at any other point along this loop. And so that would say that B has the same value everywhere along this Ampean loop. And so that's an important step in our solving the equation, because if we had not picked a circle for our Ampean loop, we would not be able to say it looked the same, and we would not be able to say it's a constant. We would not be able to pull it out in front of this integral. But what the good choice of an Ampean loop allows us to do that. So symmetry is a strong power in this solution. The other things are lines of, and I guess I'd prefer to call these lines of anti-symmetry versus symmetry. That is, if I took a line, and maybe I'll just include the point P, but it doesn't matter where the point P, but a line that would be the diameter, if you took and flipped this whole contraption, and so imagine this little circle being flipped. I guess I do have my simple animated objects here. So, imagine this nickel is the line. If you flip it over, you still get a circle, but look at what would happen to the electric field. Instead of the electric field pointing up, once you flip it over, it'd be pointing down. And so you don't get exactly the same thing around this line. You get the opposite. That's why I call it an anti-line of symmetry. So it's not a line of symmetry, it's an anti-symmetry. So you get exactly the opposite. But here then is the argument. The argument is whatever direction the magnetic field is along this line of anti-symmetry, it must be such that when you flip it, it does the opposite. So it would not be, say, in this direction. Because when you flip that, you get this direction. That is not the opposite. It is also not along the line. Because when you flip it, you get the same direction. And so those are the kinds of things we know the direction would be for lines of symmetry, not anti-symmetry. So an anti-symmetry must be perpendicular to the line. Because when you flip that, you are literally pointing the other way. So based upon our symmetry arguments, we know that this angle then must be 0 degrees, because we know that the magnetic field at this point must be perpendicular to this line of anti-symmetry, which happens to be the same direction as the tangential of the line. And that's what this ds is. So we are arguing that the magnetic field and the ds would have to be in the same direction based upon this line of anti-symmetry when we flip it. So that's the important part of our argument here. And so this becomes then just b times the integral of ds, and that would be the circumference. And so that would be b times 2 pi. And let me pause here. Since there are two circles, why don't I call this capital R? And so the bigger radius is capital R. And I just noticed I'm kind of missing my blue ink today. I don't know what I did with my blue one, but I'm kind of wondering if I need it, and or I wonder if the blue stands out better. Maybe it's about the same. Okay. So now on the other side of this equation, this says that now that you've done the integral around this green loop, okay, then it must be equal to these two factors. Now, the first factor is how much current flows through that, and that would be 0. Isn't such a good pen to use here. Let me. Yeah, this one's working. All right. So that, the 0, if you will, is what we did a lot in chapter 30. So that's really not the lesson here for this chapter. So that's why that one's just going to fade away. It's okay. Let's not pay any attention to that one for this particular chapter here. Of course, in the real world, you might have a term here and a term. But right now we have just this term. So then we have the mu naught, the epsilon naught, the derivative. And so now we are doing the electric. And it's been a long time since we did electrical flux. That showed up with Gauss's law in chapter 24. And so let's apply then those lessons. Makes a nice kind of review for the final and the end of the semester. But let me take the dot product and kind of look at the symmetries involved here, or at least I guess maybe not symmetries would be a good word there, but the directions involved, because they told us straight out with these orange dots that the electric field is pointing straight up. And dA is the area vector that we are integrating with. Now, the area vector is the area enclosed by this Gaussian loop. So coming back to this side of the equation, we did an Ampean loop. We did an Ampean loop and we then enclosed all of this. So this is saying how much electrical flux goes through this enclosed area. But my point is then the dA would also be up. And so this would be 0 degrees for that dot product. Okay. Also, the electric field, derivative, could be really thought of as two pieces. There could be the electric field that's in the smaller radius in here, and then the electric field that is outside, which is just simply 0. Well, maybe I'll do area 1 plus area 2. In area 1, there would be an electric field, but area 2 would have no electric field. In fact, maybe it was so obvious that I didn't need to write that out, but that second integral calculating the flux would be 0. There is no flux once we're talking about an area that is greater than 5 centimeters. So I just want to write it this way to emphasize that I am calculating the flux in the entire closed area of this Ampean loop. Just from 5 centimeters out to 15 centimeters, the electric field is 0 and you get no flux. So the only flux that I need to be worried about is the small circle, even though technically this is saying what is the flux in the big circle. But like I said, there is no flux beyond the little circle. So I am technically calculating the flux in the big circle, but I'm going to reduce it down to the flux for the little circle. All right, so this is mu naught epsilon naught, and then the derivative. And then I would have the electric field integrated over the area. But that's a key step because they are saying that the electric field does not change in this area. It's the same everywhere in this area. Now it changes with time. So I can pull the electric field in front of this integral, but not in front of the derivative of time. And once I do that, then I just have the area. And this would be, of course, the area of the small circle. So I'm going to represent it with a small r. It would be pi r squared. Now, calling this page 1. Now move into page 2. Page 2 would be this, b 2 pi capital R. Okay, so there's the left-hand side. Let's copy it down for the moment. But then this is the mu naught epsilon naught, so permeability and permittivity of free space. And then the area of the small circle doesn't change with time. And I'll then bring that in front of the time derivative. And then I'm just left with, how does the electric field change with time? In fact, written in this form is kind of a neat way of seeing it. This is now saying that the magnetic field is created by the changing electric field. And so you can see that a little better now in the math once we go through the details of what is meant by I guess on this side, the left-hand side, the line integral, and on the right-hand side, this flux integral. I guess it'd be a surface integral. All right, well, I guess we can now cross out a pi on each side. And then move the 2 and the capital R to the other side. And let me emphasize, notice it is saying that the magnetic field, the strength of the magnetic field is depending on how does the electric field change with time. And so they told us what the electric field was, 300, but that's kind of irrelevant. The other thing that they told us is it's changing at a rate of 20 volts per meter each second. And that's the one that's relevant for this problem. How quickly is it changing? All right, so now to put in our numbers, this is 4 pi times 10 to the negative 7. This is 8.85 times 10 to the negative 12. The smaller radius is 0.05 squared. 2 over the bigger radius, which would be 15 centimeters. So I'll put as 0.15. And the big one here is that this is changing at a rate of 20 volts per meter each second. And so I'll do the numbers here in just a second. But we might pay a little attention to the units here and confirm that they come out to Tesla. Okay. Let's see. Let's look at the numbers here. So this would be 4 times pi times 10 to the negative 7. 8.85 times 10 to the negative 12 times 0.05 squared times a 20 divided by a 2 and divided by a 0.15. Wow. That is extremely small. Now, it might be why we often neglect it when it comes to engineering. But it makes me wonder if I did something wrong, maybe hit the button wrong. Let me jump over to the solutions here. What number was this again? Number 3. Number 3 says 1.85 times 10 to the minus 18. Let me make that a little bigger just to confirm. Okay. Okay, good. All right. Being so small, I was a little bothered by it. But then on the other hand, changing at 20 volts per meter each second really isn't that much. And so we do this a lot in engineering, and we always seem to ignore the magnetic field. And so I guess that's my justification. We don't even think about the magnetic field. Way too small to really even have any effect. All right. Cool. That was a neat one. All right, let me do the next one on your list. Let's see, it's number 4. And we'll start here at 11:09 and say, ooh, let me try to save some paper. No, I'm afraid that might not be good for those of you who might be scanning the video real quick. Okay. I'd like to kind of write it here up at top. Okay, so chapter 34, number 4, page 1. Okay. All right, let's take a look at what this one says. So number 4 says, a very long, thin rod carries an electrical charge with a linear charge density of 35.0 nanocoulombs per meter. All right, so I'm going to just kind of make a kind of a long and skinny rod, as they said, a very long, okay, and thin rod. And they gave me positive numbers, so I'm going to do a little positives here. Okay. Lies along the x-axis. Oh, good. I drew it along the x-axis. And it moves in the x direction. So it's moving. So a little arrow here. It's got a velocity of, oh, wow, it's moving super fast. 15 mega meters per second. So mega is a million. So 15 million meters per second. Now, let me just pause and use this as an opportunity to make sure you haven't, missed anything in terms of this, not only this particular chapter, but all the chapters. And we've been drawing the electric fields in our kind of our burnt orange. So I'll continue with that. And so we learned that these long rods have a magnetic field that is radially outward. Now, it's kind of hard to draw this in 3 dimensions, but if this is the long rod, then the field would be radially outward this way. Use my little arrowhead here with old pencil. And so arrowhead would be pointing this way, but it would also be pointing radially outward. So in the 3 dimensions, it would be pointing up towards the camera here. And then I can lay it over and it would be pointing downward. So this is what I'm trying to draw in this picture. And this would go all the way back to when we solved this with Gauss's law in chapter 24. It's been a while, so I'm looking ahead here, and I'm glad he asked this because question A says, find the electric field that the rod creates at a point x equals to 0 and y equals to 20 and z equals to 0. So if we put a grid on here, maybe I'll just put the grid kind of at the center, but I call this the y-axis, and they definitely said this was the x-axis. Well, we're looking at, the electric field some point here that is 20 centimeters from this rod. But I was going to say, but not a Z direction. So not, not up towards the camera. So this is a nice review of Gauss's law. Let me, just perform Gauss's law. Gauss's law says if you take the electric field and add it up over a surface area, so the flux, it would equal to the charge enclosed over epsilon naught. Now, we did some Gaussian surfaces. Let me kind of try to draw a Gaussian surface. I'm going to make it here in blue and maybe make it a cylinder of length L and these end caps of area A. And let's do the flux. Now, Gauss's law says you have to have a completely enclosed surface. And so technically then, this cylinder has 3 surfaces. You remember our Gauss's law stuff. Let me grab my little sticky notes here and try to make a Gaussian surface again. And you can see it a little better on the camera, but if I kind of do a kind of a cylinder here. And imagine this closed up. There would be this rounded part and then the caps of them. So maybe I'll put cap and round to make sure I do all the surfaces. Okay. But also, our argument of our lines of symmetry, not anti-symmetry like the last problem, but a line of symmetry. And so like this y-axis is a line of symmetry. That is, you kind of imagine this long rod here, and I spin it all the way around, so a 180-degree rotation around the y-axis. Because I have positives to the left and to the right, they look exactly the same once I spin it. And so this y-axis is a line of symmetry. And in fact, if the rod is really long, any line I draw is essentially a line of symmetry. Now, technically, it's only a line of symmetry if you rotate it around an infinitely long rod. Okay, but this is a very long rod. So I'm going to use that to say then that the electric field then must be pointing along these lines of symmetry. Okay. And these lines of symmetry then are the ones that would say the electric field is pointing outward. And I point that out because, again, if you look at your caps here, the surface area would be, in this case, along the negative x-axis, and in this case, along the positive x-axis. And the electric field member would be radially outward. So that would make a 90 degrees. And so what I'm trying to say is for the end caps, I would have a cosine of 90 degrees in each term. But for the rounded parts, I would have a cosine of 0. Now, each of these would have the E and the dA in them. I didn't give myself enough room to write any of them, because what I wanted to focus on is that the caps come out to be 0, because cosine of 90 degrees is 0. And so what you're left with is just the rounded part of our Gaussian surface. E dot dA equals the charge inside over epsilon. And so that's one of the arguments we get from the symmetry of it. The other argument now is along the rounded part, you would be the same distance away. So imagine yourself anywhere on this rounded part. with a rod going down the middle. The charges would look the same. That is, the charge distribution would look the same no matter where you are on this rounded surface. And because of that, you could argue that the electric field would be the same, even though you may not even know what the equation is, and you can pull it outside of that integral. And so that's our argument. And so now we can actually do the integral. See, if we couldn't have pulled that out, we would have been in trouble because we can't actually do this integration once or with the electric field inside because we don't know what that equation is. That's why we're trying to find it. And so pulling it out helped a lot. Now, as far as the area of this rounded surface, that's probably best to look at it with the surface unwound, because now it just has a rectangular look where we have length and width. And the length we called L of it, but the width would now be the circumference of it rolled up. And so that would be the 2 pi r. Now, the charge enclosed, if I could use this pen as the charge again, it would, of course, be the charge density, the charge per length, and then how long is it? Because then that would be a lambda L. That's what's meant by charge per length. And of course, then the L's cancel off. And so it took me a while to kind of repeat this. I thought maybe it would be worth the effort of repeating it instead of just writing down the answer. But I think that would have been fine too. In fact, I kind of think maybe that's what the author was expecting, for you to just kind of jump back to Gauss's law, which is chapter 24, and to kind of look where he derived the electric field from a rod and say, okay, this is the electric field from a rod. All right. So finally, and again, really nothing to do with this particular chapter. Find the magnetic field create. That's not part of this chapter either. And then find the force exerted. That's not really part of this chapter. Huh. So I guess it's more about the two together and Hertz's discovery than really about this chapter. Anyway, it's still a good problem, but a lot of this is really past chapters. Oh, but this will allow me then to do the calculation. And this would be 1 over 2 pi times 8.85 times 10 to the minus 12. And then the charge density, they say, is 35 nanocoulombs per meter. And then the distance away, R, we said was 20 centimeters away. And so that would, in terms of meters, would be 0.2. And so I would get, let's see, across the top, 35 nano. So 35 nano, button there. Times, no, actually divide. And let me divide it by a 2. Let me also divide it by a pi. Let me also divide it by an 8.85 times 10 to the negative 12. And then finally, let me also divide it by 0.2. And so we're looking at about 3,100. I'll just do 3 significant figures. 150. And we can say these are volts per meter or Newton per Coulomb. But maybe we should go with volts per meter. And in fact, just to make sure that I did it the way the author kind of expected. Yeah, so he writes out a Gauss's law. he does a Gaussian surface, he does this and comes out with 3.15 times 10 to the third. Yeah. And and he does put the direction, I guess I should have said radially outward, but at this point that would be along the y-axis. So I should call this a j hat. All right, so there is the electric field. All right, and so there's the answer to A. B says, find the magnetic field it creates at this same point. All right, well, I guess this is where this chapter comes into play. Because we learned that the magnetic field comes from two places. One is from the moving charges itself, that is current. And now the other, called the displacement current, terrible name, is actually the change in the electric field or the electric flux. All right. Now, the reason I was saying earlier that I don't know if this is really part of this chapter, because if you come back to this kind of this mental picture, and so here's this rod of charge that's moving, and it's really long, and you're looking at this point Y, even though it's moving, you're so far from the edges, or the edges are infinitely long, that the electric field doesn't change anywhere near this. You just, move to a different part of the rod, but it's still the same field and the same field and the same field. And so for this particular problem, then the second term is zero. And this is the main point of this chapter. So that's why when I read this a moment ago, I was like, well, I don't know if this really fits this chapter. Now the charges are moving. See, because remember, there is this rod, and this rod is moving along. So there is a moving charge. There is what you might call a current due to the motion of these charges. So there would be this term, but not really this term. And this term is really Ampere's law, and we were introduced to that before this chapter. But I guess it's still this chapter because now we're looking at the totality of this equation. Anyways, I want to point out that term is going to be zero. And so now if we come back to our picture, and with my green here, and I draw an Amperean loop in green, and that's getting kind of messy, so maybe I should redraw down here. So here's this moving rod without the electric field or the Gaussian surface. And there's some point out here, point P, let's call it. But if I draw an Amperean loop and then come back up to this equation and do this symmetry argument, really it's an anti-symmetry argument. Maybe drawing in red this y-axis again. But if you imagine flipping this, now the rod's going the other way. So you get exactly the opposite motion. So that's why I call this a line of symmetry. So when it came to charges, when you flip it, it's a line of symmetry. But when it comes to the motion of the charges, and you maybe start in this direction and you flip it, so now it's going the other way, it is an anti-symmetry. And the reason that's important is, like in the last problem, we said then that the field, and so in this case must be a magnetic field, must be then perpendicular to this y-axis. And for that matter, must be perpendicular to the plane So it's perpendicular to both the y-axis and the x-axis, which makes it in the z-axis. And so this would be a k-hat direction. And so that will be important, I'm sure, in a few moments when we ask what direction is the magnetic field. But as far as the strength goes, I can just pull it out and get a B, and then I can have an integral of ds, and it's also cosine of 0 degrees. Again, the 0 degrees is the argument of, okay, what is the path you're integrating? That's the ds. Well, I'm doing a loop. Okay. But what direction is that magnetic field? Well, we just argued that the magnetic field would have to be along a line that's perpendicular to one of these lines of anti-symmetry, which go through the diameter. So, in other words, the direction of the magnetic field must be the same as the loop. So, therefore, the angle is 0. And so this whole thing reduces down to B times 2 pi r, where r is the radius of this Ampean loop, which, of course, in this case, coming back to the original picture, this would be a radius of the 20 centimeters because we're trying to find the magnetic field at this same point. I think that's how they phrase it. It says, yeah, find the magnetic field it creates at this same point. So there is the left-hand side of this equation, which is called the Ampere-Maxwell equation. Okay. And then the other side over here, mu naught epsilon naught. Oh, sorry, that one was 0. Sorry, it's this one. Mu naught times the current. Let me write the current as dq dt. So this is the rate at which the current is flowing through or racing through. Now, maybe see if I draw a small section of this rod in black and say, okay, imagine how much charge goes through here in a given amount of time. You might do something like this. You might say, okay, the charge that would go through would be the charge density lambda sometimes some distance x, x being the length of that piece going through. And of course, how long is it really depends upon the time factor. So without really specifying anything, let me just point out that since we're taking a time derivative, the lambda can go in front and you would have a dx dt. So you would have a given length for a given time. But that rate is the velocity. So this is mu naught lambda v. So that might be the hardest part of this problem, although part A might have been kind of hard too, just because you had to remember our Gauss's law stuff from quite a while ago. So now that I simplify all this, I would say B equals, and so I got this mu naught lambda v on one side, and then I'll divide it by 2 pi r. And then when I fill this out, remembering that the permeability of free space is 4 pi times 10 to the minus 7. So when I divide it by 10 to the minus 7, I just get 2 times 10 to the minus 7. This is the charge density, which is 35 nanocoulombs per meter. The velocity is that huge number. Let's see, what was it? 15 million meters per second. And the radius, or the distance away, is the distance of this Ampian loop. Okay, so this Ampian loop would be the 0.2, I believe. Yeah, 0.2. There it is. I'm back on page 1. Okay. So 0.2 meters. And so there would be the magnitude of the magnetic field. So 2 times 10 to the negative 7 times 35 times 10 to the minus 9 times 15 times 10 to the 6 and divided by 0.2. So this would be 5.25 times 10 to the minus 7 Teslas. Now, remember earlier we said that this would be in the k-hat direction. And we got that from that symmetry argument, that it would have to be perpendicular to this y-axis, but it also had to be perpendicular to the plane that this was cutting through. So that would leave the z-axis. So there is the magnetic field. And maybe I'll do the same thing. So I check to see what the author got. Yeah, I got the same thing. Nice. All right. And so now we can get to maybe the last step, which is still a pretty tricky step here, but part C says, find the force exerted on an electron at this point that's moving with a velocity of, so I draw the rod here. Remember, the rod was moving at 15 million meters per second. We have up here a little electron that they say is also moving in the x-axis. Let's see, it's moving at 240 million meters per second in the x direction. So it's actually moving faster than the rod. Okay. Quite a bit faster than the rod, for sure. Okay, so with that in mind, then, I could go ahead and say, all right, let's calculate the force. So the force would be both from an electric field and from a magnetic field. And so that's really kind of the crutch of this last step of the problem, is to realize we have both fields. We have both an electric and a magnetic. And we're going to get a force from both of those. All right, so let me just do the electrical one first. Because I know the charge of the electron is negative 1.602 times 10 to the negative 19 coulombs. And going back to step A right here, we said the electric field is 3,150 in the j-hat direction, and I guess we could write it as newtons per coulomb, so that the coulombs cancel off and you're left with just newtons. And notice it's a negative j-hat direction, and that makes sense. Coming back to our page 1, we said the electric field was pointing radially outward, so that would be up here, and you put an electron gets pushed opposite of a field, so it would be attracted towards the positive, and that would be the negative j-hat direction. And so if we grab a calculator, 1.602 times 10 to the negative 19, and we multiply it by 3,150, we would get a force of of 5.05 times 10 to the minus 16. I'll put a little circle around it. And so that would be the amount of force just from the electric field. The harder part of this Lorentz force is right here, the V cross B, which, since it's a cross product, let me write it as QVB sine of the angle between them if I just want to get its magnitude. I'll worry about its direction in a moment. Well, let me just worry about its magnitude. Okay. So if I'm just worried about the magnitude, I don't have to worry about, any negative numbers here. So I'm going to put 1.602 times 10 to the negative 19 for the charge of the electron. The speed was given here as 240 million meters per second. The magnetic field is what step B was all about. 5.25 times 10 to the negative 7. And the sine is the angle between V and B. And it's 90 degrees. Maybe we should come back to the picture here. Remember, we said that the magnetic field is in the Z direction. And we also started this problem saying that the motion of the electron is in the X direction. And so the Z and X direction are 90 degrees apart. And sine of 90 is just 1. All right, so this would be I should have put the magnitude on the outside there. Okay, so this is just the magnitude of it. So let's see what we get in terms of its magnitude. 1.602 times 10 to the negative 19 for the Q, 240 million for the speed, 5.25 times 10 to the negative 7 for the field. And we come up with 2.02 times 10 to the negative 17 newtons. Now let's do the direction. So B is its magnitude, then put a vector over it, its direction. And so remember, it would be V cross B then times a negative. Okay, so I have here a V in the X direction. And so the X direction would be this way. So I need to get my right hand, but somehow switch my right hand around so that my fingers are pointing in the direction of X. Okay. So there is V. Now B would be coming in the Z direction. I'll call the Z direction towards the camera here. So the V is in the direction of my fingers. If I close it in the Z direction, well, that would be an X cross a Z. I would get a negative Y direction. But multiplying it by a negative for the electron would make it a positive Y direction. So I would say that this is in the positive J hat direction. Okay. So if I put these two together now, I would say then that the total force is a negative 5.05 times 10 to the minus 16 newtons in the J direction, and an upward 2.02 times 10 to the negative 17 J hat. So I got to add those two vectors together. So taking this one here. Oh, I need it with a negative. So times -1. Okay. So taking 5.05 times 10 to the -19 and adding to it this number here and hit enter. Still get a negative, makes sense. That one's a little bigger, of -4.84 times 10 to the -16 newtons. And let's see what they got. They got a negative. Good. J hat. Oh, I didn't put my J hat here. And they got 4.83 times 10 to the -16. Good. Nice. I agree. All right. Hey, well, guys, I know that there's a bunch more. Let me cross this one out here. What number was this? Number 4. Oh, that was a long one. But it's time for our first break today. So unless anybody's in a rush here, let me just check the chat room here. Okay. Josh, I did see you haven't thrown anything in the chat room, so you're probably just following along. Yeah, okay, good. All right, great. But let's take our break here and we'll come back a little less than an hour. So it looks like we got 45 minutes. We'll come back and continue on this list. I got number 9, 11, 16, 20, 25, 28, 31, and 32 still on my list. So quite a few of them. All right. See you 45 minutes.